right? We will have another circle over here, right? So this is one circle. And then we have an even bigger circle, yes or no? Right? We have an even bigger circle, and this circle is the actual circle that is going to ruin the material. Right? So if you were to just look at the blue circle, this circle over here, right? The tau max will be equal to what? The tau max will be equal to 150 minus 25 divided by 2. Okay, so 150 minus 25 divided by 2 will be only 62.5. If we were to look into the bigger circle, right? Tau max is equal to 150 divided by 2, right? And this is equal to what? 75 megapascal. That is why it's important to what? Construct this using what? 3D mold circle. Are we clear? Okay. I have another example. Okay. So we know that under this loading, right? The material will what? The material will yield. Now this is very obvious even without drawing the mold circle, you know, will yield. Even my mom could tell. Why? Because this is at what? 150, yes or no? Right. Let's do something. Yes. I'm going to do that next. Okay, so for this case, usually you will fail by shear first. Most material will fail by shear first. Okay, because the shear has a lower magnitude than normal stress, not normal. Okay. The next condition that we're going to look at, which we can't tell, or we're going to do this problem. This problem is like super bombastic. Okay, you will go super fantastic and bombastic. You will love it. I can't wait to show you this. Okay. So let's look at the next one. Right, again, we have a box down here. Right, and now this one is have 75 megapascal. And then it has what? 50 megapascal. Sorry, I'm going to do this in 3D again. Okay. And again, the same thing, the stress yield is equal to 100 megapascal. And if we were to sketch this using Tresca criteria again, normal stress, shear stress, 50, 100, 150, minus 50, minus 100, minus 150, 50, and 100. And then this is minus 50, minus 100. So we are going to sketch our red box again. Here we sketch our red box again. Right, our red box. What was the scale I used before? It's the same. Okay, so we sketch our red box. So now, if we were to look at our what? Our normal stress. By looking at our normal stress, this is one we can't tell. Okay, so over here, this point over here. So this is our point X, our point Y, and our point Z. So over here, this is our point X, right? And then we have our point Y. And then at the center here is our point Z. Okay. So if we draw the circle for the XZ plane, right? So if we were to draw the circle for the XZ plane, it looks good. Yes or no? We are within the box. If we draw the circle for the what? YZ plane, right? If we were to draw the circle for the YZ plane, it seems fine, right? However, we have another circle which is on the what? XY plane. So now we were to sketch our circle on the XY plane. What happened? 3, 5, 2.5. What do you see? That the circle is greater than box. So this is outside the what? Outside the box. Okay. So for this case, the material, the what? It's not so obvious. For this case, the material will yield under the above loading conditions. Right? For this case, you can't really tell. You have 75. You say 75 is here is it's less than 100. And then 50 is also less than 100. But when you draw sketch into 3D mode circle, you can see that this is going to what? Yield. As long part of it is outside the box, we will yield. Okay. So next, I'm going to sketch the operating boundary. Okay, we're going to sketch the operating boundary for Tresca criteria. Okay. So now we are going to draw a different box or different diagram. So on this diagram, you also have an x-axis, and we are also going to have a y-axis. Now the two axes are labeled differently now. Okay, so what is the difference? This is labeled as stress A, and this is labeled as stress B. Okay, so we know that stress A and stress B are the what? Are the principal stresses. Then from here, I'm going to put down stress yield. Okay, so this is our stress yield. Over here is our minus stress yield. And the yield is acquired from what? Experiment. Anything that is yield is acquired from experiment. So from here, we are going to sketch a box or a boundary. Okay. So this is our boundary. So in this boundary, anything that is inside the pink will not yield. Where you see I'm shading the pink. Okay, where I'm shading the pink. So anything that's inside here, what will happen? Will yield or will not yield? So it is the what? Operating bracket. Okay, so this is the operating bracket. Okay, so if your stress state, your stress A and stress B, so let's say now your stress A and stress B are here. You can see, right? I'm colorblind, I can't see shit, but anyway. If all your stress state are inside here, right? It shows that yielding will not occur. When yielding will not occur, you can calculate your full of shade, no, factor of safety, which is equal to stress yield divided by stress A or your stress what? B. Are we clear? If anywhere that is outside, okay, any of your stress state that are outside, right? For this case, yielding will occur. When yielding will occur, do not calculate what? Factor of safety. Are we clear? Okay. In the exam, I might ask you, okay, the material has already been yielded, and I still ask you to calculate factor of safety. If you give me the number, I will minus 2 marks. Okay, because it's yield already. What? How fast it yield? Ridiculous, yes or no? Right. Okay. Enough theory. Let's go into my favorite problem. Okay, let's look into this problem now. So this problem is not that it's not difficult, but it has a lot of what? It has a lot of layers. Come on, Eugene, what are you doing? Paper size. Okay, it has a lot of layers. Okay, and let me describe what is this layer. So we're going to look into this problem, and let's look at this problem. Okay. This problem was used to be a final exam question. Used to. I repeat again, used to. Okay. The internal loading at a critical cross-section along a steel shaft of a ship are calculated to be a torque of 2,300 pound-feet. So this question is very kind. It says that this is the torque. But if this was not given, can you realize that this is a torque? Yes or no? How? How do you know it's a torque and not a bending moment? Remember what I taught you? When the torque is applied, the centroid did not deform at all. Yes or no? Right? The centroid is still at the what? So the centroid of interest is this centroid over here. Remember? So when we twist that centroid, because of zero radius, it will not deform at all. But this question is being very kind. And over here, we have our bending moment. And over here is our what? Axial what? Axial load. But what is so tricky about this question? Anyone? Why this question is tricky? Can anyone tell me? I can't give you money now because the wife took everything from the wallet this morning. But what is missing? Evans! What is missing? Or anyone? Daniel, good morning. You don't come for my my Tuesday morning lectures. I don't know why. Don't hide. Everyone know that you're Daniel, okay? Yes. Where the element is? What sort of element do you want to know? You're partly right, okay? This question looks innocent, but and this is what true engineering is all about. Where failure will what? Will occur. Yeah, again, they don't tell you. Okay, you have to go fish. Yes or no? Go fish. Go fish is the swimming club, but anyway. So over here, we know that this is our X. This is our Y. And this is our Z, right? And we know that if the bending moment is going this way, over here is what? Compression. Below here is what? Tensile. This axial load is going to be inducing what? Compression. Yes or no? So the element that we want to select must have the maximum what? Compression stress. Well done. Okay, so the element we need to determine the location where what? Normal stress mean is at the largest what? Magnitude. Right? So from here, this is our transformation, this is our Y, this is our Z, this is our rotation about X. Then we start sketching our element. So this is our element. And this is where the center lines are. So I'm going to place our element now. Element I, J, K, and L. And what we have known, or what we already know, that we have a what? This is our moment in the what? In the, oh, did I got this wrong here? Y and Z. Yeah, this is our moment about our Z-axis. Okay, this is our moment about Z-axis. I'm trying to figure out what is wrong down here. Yeah, I'm okay. I labeled this wrongly. Okay, I should label this. This will be our Y. This will be our Z. Am I right? Y, Z, and then this is our X. And then this is our rotation about X. Wait, I'm not getting what I'm not getting right. No, this is our moment about Z. Okay, I'm rushing now. I'll stop here. I'll see you guys tomorrow. Yeah, I'm getting something wrong down here. X. Ah, it's correct. The axis is correct. So that is our moment about Z. Yeah. I'll see you guys tomorrow. Tomorrow, no, Thursday. No, Friday. Yeah.